Okay, we are off to chapter 14. Uh, then we'll have a little lab, a little exam, and then call it a week. Oh, not bad. All right, so chapter 14 is about liquids and solids, and we're going to talk mainly about liquids in this chapter. So the first thing we're going to talk about is water and the different phases that we see with water. And water is obviously a colorless, tasteless substance. It freezes at 0 degrees Celsius. It boils at 100 degrees Celsius. Hopefully you know that, but you do need to know, obviously, its boiling point, which again is 100 degrees Celsius, and obviously its melting point there, which is 0 degrees Celsius for water. Water expands when it freezes, and one of the properties we talked about with water is, typically speaking, if you do need a density value for liquid water, usually we use 1 gram per milliliter, and that is usually pretty go-to sort of number there if you do need the density of water. As a reminder, as we talked about when we did density, way back whenever we did density, it does change with temperature. And so technically speaking, if it's not 25 degrees, it will be a slightly different number. But usually for book or book type problems or any type of calculation you're doing, if you find yourself in a need for the density of water, then 1 gram per milliliter is typically the number that you use. Also, a reminder as we sort of transition from one point to the next. So if we have something like solid, right, everybody is packed in there pretty tight. As we have liquid, everybody is still relatively tight to each other. They have a little bit more energy in this case, so they can kind of flow around each other. And that's why, again, liquids are fluid. And when we get to the gas phase, everybody has completely broken apart. Now, we're going to talk about energy associated with sort of these transitions, and a reminder that as we kind of go from solid to liquid to gas, those are all processes where you have to put energy in. And again, that is obviously, as we talked about in a number of places, what is known as being endothermic. So energy has to be absorbed in this case. So if you just take a simple example of like the ice cube, obviously when you take ice, say, out of the freezer, the room temperature is a hotter temperature than the ice itself. And remember, as we talked about in the energy chapter, energy and heat will flow from hot to cold. So your ice cube there will pick up all the energy and start to melt. Obviously, if you have liquid water and you want to sort of get it to boil, you can put some fire underneath it, right, and heat it up, and it will start to boil at its boiling point, like you were making maybe like pasta or something like that, water there to cook it. And that all requires energy being put in. And that is the opposite of what's sort of happening as we kind of go in this direction. Again, as we go from gas to liquid to solid, again, those are all processes that are exothermic. And that means that, again, energy has to be released. And again, if you have gas molecules that are flying around with a lot of energy, obviously, if you kind of lower the temperature or release the energy, those gas molecules are not going to be able to fly around as fast. As they sort of collide, they'll kind of group up because they don't have enough energy really to kind of escape each other. And as you continue to remove energy, they will continue to sort of lock themselves down into the solid phase. And one of the interesting properties of water in terms of density is, as you can see there, the density of ice is actually less than the density of liquid water. So um, that's a very unusual sort of characteristic of water. Most substances in their solid phase is more dense than in their liquid phase. And what happens, as we'll talk about a little bit, is as the water molecules basically bond with each other, what ends up happening is they create a lot of open space between the different water molecules. And by creating a lot of open space between different water molecules because they don't have enough energy to get super close to each other. And they're actually held by really strong interactions. They just can't like pile right onto each other. So they have a lot of distance between the water molecules in the solid phase. And if you just think about the density formula that we saw way back when, density is mass over volume. So the result of them not being able to get really close to one another is it really bloats the volume there of ice. And because this number gets large, we actually see the density of ice go down a little bit more than we do with liquid water. Because in the liquid water stage, even though they're still held together by the same sort of strong intermolecular force, they have a little bit more energy. So they're able to kind of move themselves a little bit closer to one another. It doesn't create these big open spaces between them. Now, this is a heating or cooling curve, and this really describes sort of the different transitions that occur here. And when we talk about the transitions, as we go from solid to liquid, that is the process of melting. As we go back from liquid to solid, that is the process of freezing. As we go from liquid to gas, that is the process of evaporation or vaporization. As we go from gas back to liquid, that is the process of condensation. And lastly, we can go, as we talked about, I think, way early on as well in the semester, you could go directly from solid to gas, again, skipping the whole liquid part of the mess. And this is what is known as sublimation and deposition as we go from gas back to solid. And again, everything sort of with the right-hand side arrow there heading to the right, as we just talked about, are endothermic processes, and everything heading back in the other direction are exothermic. Remember, as we talked about in terms of energy and exothermic and endothermic, in terms of energy values, endothermic are positive values, exothermic are negative values. Remember, it's the same energy to do this. By the way, all of these transitions happen at the same temperature. You actually have both phases sort of happening at that exact temperature. For example, at 0 degrees Celsius, it's not until you get a little bit above 0 degrees Celsius that you actually transition to liquid water, not until you're a little bit below 0 degrees Celsius that you transition to solid ice. Exactly at 0 degrees, for example, you do have both phases happening at the same time. So it's known as being in equilibrium with each other, sort of like ice crystals. So there's some solid and some liquid water sort of happening at the same time. So again, this is a heating curve going from solid to liquid to gas. This is basically solid. This obviously is the liquid part, and up here is the gas part of this curve. And that's all endothermic as you go that way, and exothermic if you're starting on the top, going to the bottom. That is what's known as a cooling curve. So when we talk about these transitions that occur, there is a certain amount of energy required to do nothing more than just simply take a substance from one phase to the next. So, for example, at 0 degrees Celsius, there's a certain amount of energy required to take ice at 0 degrees Celsius to basically liquid water at 0 degrees Celsius. So that's basically this transition, not changing the temperature or anything like that, but just simply to take it from one phase to the next. And that energy that's required to do that is known as the heat of fusion, and that is sometimes abbreviated as the delta H of fusion. If you remember, we talked about delta H in that energy chapter. That's the change in enthalpy. That is the energy sort of change for a reaction. Again, a reminder that when you see a delta H, if it is positive, it is an endothermic process. And if you have a delta H that is negative, it is a exothermic process. Now, for ice, which is obviously water, That energy is about 6.02 kilojoules per mole. That is delta H of fusion for liquid water. That is roughly approximately 335 joules per gram. And that is just a conversion from, instead of kilojoules per mole, to joules per gram sort of conversion. The energy required to basically change a mole of liquid vapor and doing the transition from liquid to gas, or gas back to liquid. By the way, the heat of fusion here is the transition from solid to liquid, or liquid back to solid. That also requires a certain amount of energy. And for example, this is for water. That is what is happening right around here at 100 degrees Celsius. That is the normal boiling point of water. And again, at exactly 100 degrees Celsius, you have both phases happening at once. You have water, liquid water, and steam sort of happening, and steam and liquid water. Sort of what happens at the surface of liquid water. Some of it jumping out into the gas phase, some of it's dropping back into the liquid phase. So you have that happening at that point. And that is the transition required to do that, is the molar heat of fusion, heat of vaporization. So this is the delta H of vaporization, is sometimes referred to. And for liquid water, that is 40.6 kilojoules per mole. That is roughly 2260 joules per gram, is a joule per gram sort of version of it. Now, this again is the energy required to simply take that liquid water at 100 degrees and change it to steam or gas at 100 degrees. Again, not changing the temperature or anything like that. Now, again, this occurs for the fusion. That obviously occurs for water at 0 degrees, which is a normal melting point of water. And obviously, the heat of vaporization occurs at 100 degrees, again, for water. And that is his normal boiling point. So these numbers here are some numbers you do need to probably know along the way here. So kind of know these guys. And it is also important to remember, although we actually see these numbers a lot, and a lot of times we deal with water sort of in these examples, it's important to remember that if the substance you're dealing with is not water, these numbers would not apply to those substances. So if you're dealing with some other substance other than water, they will have different heat of vaporizations, different heat of fusions. They will also, by the way, have different melting points and boiling points. So when we talk about 0 degrees Celsius as a melting point, or 100 degrees Celsius as a boiling point, that is specific for water. So once again, if you happen to be dealing with something that is not water, you really probably shouldn't be using these numbers. You would have to perhaps go to look up on a table or something like that the appropriate heat of vaporization, heat of fusion for that substance, and also the appropriate boiling points and melting points. So how does this sort of work in relationship? This sort of energy change that occurs at the different phases also ties into something that we saw in chapter 10, the energy chapter, which is our friend specific heat. And if you remember our specific heat equation, Q is equal to ms delta T. And remember that here Q is energy, our heat. And usually the units there are joules or calories. M is the mass, and usually the units there are grams. Delta T is our final minus our initial. Remember that when we use this equation, this is one of the few times that we actually don't convert our temperature to Kelvin. So we do keep it as degrees Celsius. And the reason we do that is the specific heat of water, which is something that you should know. For example, the specific heat of liquid water is 4.184 joules per gram per degree Celsius. But the units here for specific heat capacity are those units, joules per gram per degree Celsius. They could also be calories per gram per degree Celsius. So Why do I mention this equation? Because this equation and also the sort of heat of vaporization and the heat of fusion are oftentimes used together. And if you were going to calculate, for example, how much energy is required to change like ice into liquid water at a specific temperature, you sometimes will have to use these sort of equations and formulas together. So the way to sort of remember and sort of think about, which one should you use in what situation is when we talk about heat of fusion or heat of vaporization, these things are used when basically the temperature stays the same, but the phase changes. So if you have any situation where the temperature is the same and the phase changes, then you're probably going to use a heat of vaporization or a heat of fusion. Specific heat is all about basically changing the temperature and keeping the same phase. So that is why in earlier examples, for example, we want to know how much energy is required to heat up water from like 20 degrees to 30 degrees. At 20 degrees or 30 degrees, water is still going to be in the liquid phase the entire time. And we would use a specific heat equation to do that. If we wanted to know how much energy is required to melt an ice cube at 0 degrees to basically liquid water at 0 degrees, the temperature doesn't change, but the phase changes. We would use something like the heat of fusion to do that. And remember that enthalpy, energy, these are state functions, so it doesn't matter if it takes multiple steps. What matters is sort of where you start and where you end. So if we have to do sort of a multiple step type calculation that involves energy, if we want the total energy at the end, we just simply add all the steps together. So all the energy steps just gets added together, and that gives us our total energy required to do that transitions. Any questions on that there? All right, so why don't we take a look at a problem here where we kind of pull all this stuff together. So we'll take a look at this. And in this particular problem, what we are looking to do is we want to know how much energy is required to take 75 grams of ice at minus 3.5 degrees Celsius to steam at 102 degrees Celsius. So ultimately, we're going to start way down here on this graph. We're going to start way down here, maybe, at minus 3.5 degrees. We eventually want to get all the way maybe up to here at 102-ish. It's probably way more than 102. Actually, 102 probably way, but that way. We want to get all the way up to that part of our curve here. So there is several sort of transitions that occur when you do this, and you have to take a calculation like this sort of step by step and sort of see what you're doing. So for example, the very first thing that would occur in this case is we would have to go from ice at minus 3.5 degrees Celsius to basically ice at 0 degrees Celsius. So that would be the very first step that we would do. So let's take a look at that. We're going to go at the very first step here. We're going to take ice, which is solid, obviously, at minus 3.5 degrees Celsius. I feel like I lost a 0 there. To ice, which is still solid, at 0 degrees Celsius. Now, why did I choose 0 degrees Celsius? Once again, this is water. So its normal transition from solid, which is ice, to liquid occurs at 0 degrees. So I got to kind of get myself up to 0 degrees so that I could then do the transition from solid to liquid. Now, when I look at this, how do I know what I should use? Well, in this case, that's a solid, that's a solid. All I'm doing is changing the temperature. The phase is solid all the way through. So that tells me I should use my specific heat equation that we saw in that earlier chapter. And we would put in our numbers here. So this is going to be 75 grams of ice. Now, a very important thing to remember is this. You had to remember the specific heat of liquid water is 4.184 joules per gram per degree Celsius, or 1 calorie per gram per degree Celsius. But that is actually liquid water, and we're not currently at liquid yet. We're actually in the solid state. And the specific heat for water in the solid state and approximately the specific heat of water in the liquid state are a little bit different. It is actually approximately 2, we'll call it, joules per gram per degree Celsius. And this one is also approximately 2 joules per gram per degree Celsius. I think it's 2.01, so it's very, very close. So it's really important as well, a reminder that when you're using the specific heat equation, and you look up, for example, the value for a specific heat capacity, that you not only find the substance, but you want to make sure it's in the right phase. I would say probably water is the most common one that you have to worry about. So we'll just use the rough estimate here of about 2 joules per gram per degree Celsius as a specific heat of ice. Remember that always when we do change in temperature, it is the final temperature minus the initial temperature. So in this case, it is 0 degrees Celsius minus a negative 3.5 degrees Celsius. Again, those two negatives are going to turn my energy value into a positive number. And we will end up with here 75 times 2 times 3.5. We're going to end up with 525 joules of energy is required basically just to do that first step. It is, again, a positive number, which means it's endothermic like we would expect. We're basically heating up the ice and trying to get it to dissolve, basically. And in order to move that ice from minus 3.5 degrees to 0 degrees ice, you got to put in there about 525 joules of energy. Any questions on that there? So that's a very similar calculation to what we did in that previous chapter. Now, if we take a look at our map, we are now going to be sitting at this point right about here. So we're at 0 degrees Celsius. And the next thing that's going to occur is we're going to have a phase change. So we're going to take it from basically ice, which is solid, to basically liquid water. And once again, this is going to occur at its normal melting point, which is 0 degrees Celsius. It is a flat line, which means we are not changing the temperature. And this will be our second sort of step along the way. So let's take a look at that. So the second step is, now that we're at our normal sort of melting point, we're going to take liquid water at 0 degrees Celsius to, I'm sorry, no, we're at ice. Didn't get to liquid yet. We're getting there. We are at ice to liquid water at 0 degrees. So again, this is this normal melting point that this is going to happen. So at this point, we are at 0 degrees. We're going to stay at 0 degrees Celsius. We're not changing the temperature here. So that is a heat of vaporization, a heat of fusion, and that is going to be the delta H of fusion. And that is what we use as we do that transition in either direction. So we use fusion to go from solid to liquid or liquid to solid. So really in this case, we haven't spilled anything, hopefully. So we have still 75 grams of water. We're just going to use the heat of fusion. I'm going to actually use the joule number since all my other numbers are in joules, so that way everything will be in the same units. You could use the kilojoules per mole number, but you'll just be in different units. So approximately that's 335 joules per gram, and that is the heat of fusion. Basically, again, for liquid water is what we're looking at there. And if we do that, we're going to have 75 times 335. 25125 joules in this case. So that is the amount of energy required to do nothing more than take my ice that's sitting at 0 degrees and just turn it into liquid water at the same temperature. So again, not changing the temperature, need about 25,000 joules of energy to turn my ice cube into basically liquid water. Any questions on that there? At this point, if we look at our little graph here, we are now sitting right down here at 0 degrees liquid water. The next thing that's going to happen is we're going to go all the way through here up to our next transition point, which is 100 degrees Celsius for water. And we're basically going to take it from liquid water at 0 degrees to liquid water at 100 degrees. So that is sort of our next big transition that's going to occur here. So we're going to take it from, take liquid water at 0 degrees Celsius to liquid water at 100 degrees Celsius. And once again here we are changing the temperature, but it is the exact same phase all the way through there. So all the way through that line that goes up, it is liquid water. So that is going to be our Q is equal to ms delta T. And here we'll put in our numbers. We still have our 75 grams of water. We haven't dropped it. At this point, though, we are at liquid water, which means we will go to our normal specific heat capacity for liquid water, which is 4.184 joules per gram per degree Celsius. Once again, going to do final temperature, which is 100 degrees, minus our initial temperature, which is 0 degrees. And that's going to give us the energy basically to take our liquid water from 0 to 100 degrees. And that is going to end up being something like about 31,380 joules of energy. 31,380 joules of energy is required to do that transition right there. Once again, pretty much the identical calculation we did with specific heat capacity here. All right, we're almost there. We're now sitting really with our water at 100 degrees Celsius. We want to get it to steam, which is really our next transition. So if we take a look here, go back, we are now going to be in this ballpark here, I think. We are sitting right here at 100 degrees Celsius. The next thing that has to happen is we do have to transfer the phase from liquid to gas, basically. And that is going to take it at its normal boiling point, liquid water at 100 degrees to steam or gas at 100 degrees. And that would be our fourth sort of step here. We're going to take liquid water at 100 degrees Celsius to steam, which is gas at 100 degrees Celsius. That is the normal boiling point of what is occurring here. And because of that, we're going to use the transition that occurs as we go from liquid to gas in this case. That is the delta H of vaporization. So it's going to be the delta H of vaporization we're going to use. I once again am going to use the joule value here for water, so everything's in the same units. So we're going to take our 75 grams of water. We're going to hit it with the heat of vaporization, and that's going to be something like 2260 joules per gram. And we're going to end up with about 169,500 joules is the energy required to take it from liquid water to gas. Now, if you take a look at the comparison of how much energy is required to go from, say, solid to liquid, it was only about 25,000 joules of energy. But now that we're trying to do the transition from liquid to gas, it's about 169,000. Much, much more energy is required to do that second transition. Because if you think about what's happening as you go from solid to liquid, in the solid phase, everybody's pretty close to each other. In the liquid phase, they're still relatively close to each other, just a little bit more energy. But when you do that transition over the liquid phase where they're kind of close to each other with a little bit more energy to the gas phase, in the gas phase, everybody is broken apart from one another. They're flying around crazily. They're nowhere near each other. So it takes a lot more energy to kind of get everybody apart from each other, get them into the gas phase so they have that energy to fly around. And we also see that on our graph. You can see this is the energy transition for going from liquid to gas. It is a much larger transition than what we see on the bottom, which is our transition of going from solid to liquid. And again, it's just the idea of everybody's got to completely get apart away from each other. They also has a lot more energy so they can fly around once they do break apart from each other. So it just always takes a lot more energy to do that transition than it does going from solid to liquid. Any questions on that there? All right, we're almost there. We are currently sitting at liquid water at 100 degrees Celsius. We want to, though, end up at steam. I'm sorry, we're currently sitting at steam at 100 degrees Celsius. We want to end up at 102 degrees Celsius. So we actually have one last transition here that is happening, and we're basically sitting right now about here. And we do want to come up, just a little bit there to kind of finish it out. And this is going to be the very final sort of step here. And I'll go to the next page here. So our fifth and final step is taking steam, which obviously is gas, at 100 degrees Celsius to steam that is still gas at 102 degrees Celsius. So once again here, the phase is exactly the same, but the temperature here is changing. And that means that we're going to go with our specific heat equation one more time. And we will put in our mass of 75 grams. Remember here that we do want to use the specific heat for water or steam. And again, that's approximately 2 joules per gram per degree Celsius. It's not negative or anything, that's just approximately. And so we'll just kind of use the 2 number here, joules per gram per degree Celsius. Again, final temperature 102 minus 100 degrees Celsius. And that is going to get me here 75 times 2 times basically 2. It's going to give me 300 joules of energy is required. And now we have done all of our transitions. So how do we know the total energy? So the total energy is basically, in this case, just add up each of those steps. So we would take, it would equal step 1 plus step 2 plus step 3 plus step 4 plus step 5. So if we pop in some numbers here, we got 525 was our first step. And then we had, looks like 25, 125 was our second step. Then we had 31, 380. Our third step. Our fourth step required 169.5, 169,500. And our last step required about 300 joules. And again, this is really the reason as well as why I use sort of joules for the heat of fusion, heat of vaporization. You don't want to be at this step here and adding up some units that are some numbers that are in joules and other ones that are in kilojoules, because you will be off in your answer. So you just kind of want to get everybody in the same units. So we're going to go 525 plus 25, 125 plus 31, 380 plus 169, 500 plus 300 here. And that's going to get me here 226,830. And at this point, if you want, you can bring it back to kilojoules. 1, 2, 3. So that's roughly about 227 kilojoules of energy. Once again, this is a positive number, which is what we would expect to happen because all of these processes are endothermic. They all require energy to be put in, and you should end up with positive numbers really for all these steps. Any questions on that? So when you do these type of calculations, it is sort of a combination of what we did in that chapter 10, specific heat, and also these phase changes that can occur as you're going from one sort of phase to the next as you transition melting points, freezing points, boiling points. So once again, sometimes it's a really good idea just to draw a little curve like this, and that we can kind of visually see all the steps. But essentially, if you look at a curve like this, anywhere on this type of curve, if you sort of draw it to help you out, anywhere where you are kind of going upwards. So again, this is all parts where we're in the same phase, but basically changing temperature. Those are all spots where it's all the specific heat equation is what you want to use. So those are all the spots where you should use your equation that we saw previously, Q is equal to ms delta T. So anytime you're on any part of the curve in those sort of situations, that is where you want to use it. Anytime you're transitioning, which again should happen at the normal melting point, should happen at the normal boiling point, those are all spots where you're going to either use your delta H of vaporization or your delta H of fusion. So those are spots where you use delta H of fusion if you're going from solid to liquid or backwards, are the delta H of vaporization if you're going from liquid to gas or gas back to liquid. So sometimes visually it's a good idea if you have a problem like this just to sketch up a little curve like this so you don't miss any of the steps along the way. And those are sort of where you use those sort of formulas. Any questions on that there? Now, if we have this exact same problem, but we were actually starting with steam at 102 degrees and wanted to go all the way back down to ice at minus 3.5 degrees Celsius, really the only difference is all these numbers will be negative. So if you were going in the reverse direction, the energy is exactly the same at each of these steps, but the numbers should come out negative. So if you're kind of going in the reverse direction, this guy right here would flip around and that would turn this guy into a negative. And here, this would become a negative because you're going in the opposite direction, which would turn this guy into a negative. This guy would flip around because you'd be going from basically zero, ending up at 0 and starting at 100, and that would turn this guy into a negative. This guy would be a negative value if you're going in the opposite direction. And lastly, this guy would also be flipped, which would turn this guy into a negative. So if you're going in the opposite direction, starting as steam and ending at the ice or the solid, everything would be the same, except that they would all be negative because those are all exothermic processes. So again, it'd be exact same calculation, just the sign would change. Any questions on that there? All right, the next thing we're going to talk about is intramolecular forces and intermolecular forces. And the first thing here is intramolecular forces. Intramolecular forces are the forces within an atom, our molecule, that holds it together. So for example, if we took one single water molecule, these bonds here between the oxygen and the hydrogen are covalent bonds. We are sharing electrons. And those are intramolecular forces. They're basically the force that holds that one water molecule together without it just kind of falling apart or breaking apart. Covalent bonding, also ionic bonding, that sort of electrostatic attraction between the positive and negative, is what holds like an ionic compound together. That is also an intramolecular force. They are usually fairly strong interactions because If they were not strong interactions, everybody would fall apart and break apart into like alphabet soup, and everybody would just fall apart. So they're relatively strong, that's able to hold each individual sort of molecule together. Now, that is different than intermolecular forces. Intermolecular forces are the forces that hold one molecule together with another molecule. So intermolecular forces are, for example, when you get, say, a couple or more water molecules together. Water, which is a polar molecule, means that it has a charge on one side of the molecule versus the other. So on water, hydrogen is more positive, oxygens are more negative because of that. So when two water molecules get together, they bond to each other through opposite attraction here. The positive side of one water molecule is attracted to the negative side of another. That essentially is, no matter what type of intermolecular force you come across, that is essentially how all intermolecular forces work. The positive side of one molecule is attracted to the negative side of another. So it can be all kinds of different types of intermolecular forces, but they all share that common sort of feature that basically just positive and negative attraction. And this is a intermolecular force. And as we'll talk about, this is actually what is known as hydrogen bonding. And that is a type of intermolecular force that water molecules use with other water molecules to hold them together. Now, as I mentioned before, intramolecular forces are always stronger than intermolecular forces. And we know this just based on water as an example. When you go to heat up water at its normal boiling point of 100 degrees, the bond that actually breaks is this bond here. So as you heat this up at, say, its boiling point, that bond between these two water molecules are actually the first things that break, and that allows these water molecules basically to go off into the gas phase. And we know that is what occurs because when we do that, we produce steam. Now, if the intramolecular force, the force within the individual molecules, were actually weaker than the intermolecular force, when you would go and heat up something like water, what would happen is all the bonds within each molecule would start to break, and you would start producing hydrogen gas and oxygen gas. And that does not happen when you heat up water. You don't get hydrogen gas or oxygen gas. You get basically steam, which is still water. So we know definitely that each individual water molecule stays intact. And what ends up happening is they just kind of break apart from each other rather than each individual molecule just completely breaks apart. Any questions on that there? All right. So again, molecule to molecule, intermolecular forces, that is how pretty much all molecules interact with one another. It is also the basis for things like melting points, boiling points, high or low melting points or boiling points. It is also the basis for how one molecule can interact with another and whether or not they will mix together really well or not mix together really well. They'll be soluble or insoluble with each other. So intermolecular forces plays a really big role in those type of issues. Melting points, boiling points, solubility, do things mix, do things not mix. So we're going to talk about some different types of intermolecular forces. So these are all intermolecular forces. Again, the forces between molecules. The first type of force is dipole-dipole interaction. And dipole-dipole interaction is a relatively strong sort of force here. Um, and It is what happens typically when two polar molecules come together. Perhaps you remember this word dipole. We saw it when we have like a polar molecule like water that has a net dipole moment, right? So a net dipole moment only occurs in polar molecules. And what that means is, if you remember, if something has a dipole moment and it's a polar molecule, it means overall the molecule has unequal sharing of electrons, and there is a positive side to that molecule and a negative side to that molecule. So overall, a polar molecule will have a positive and a negative side to it. No matter what you do to that polar molecule, because it is polar, it will always have a positive side and a negative side. So, in a sense, polar molecules are really good to go with this type of interaction. They got positive, they got a negative side, they're ready to sort of do this type of interaction. They're only as about 1% as strong as covalent or ionic bonds. And again, that is basically intramolecular forces. So they're much weaker than those things. So basically, what happens in this case is when you get two polar molecules together, this is how a polar molecule and a polar molecule can interact. And this is usually described as polar molecules that cannot hydrogen bond. And this would be the main intermolecular force for this type of guys. And we'll talk about in just a second what can hydrogen bond and what cannot hydrogen bond. But this is kind of the main force for your polar molecules. So essentially what happens is, again, we have a positive side and a negative side. We got a positive side and a negative side of two polar molecules. And that gives them a nice little place where they can interact with each other and basically held each other together. When you get a lot of polar molecules together in something like, say, the liquid phase or even the solid phase, but mainly liquid phase as well, whatever you do, you are going to eventually get kind of like a positive side near a positive side, which is not really great, or a negative side of a molecule near a negative side of a molecule, which doesn't like to be near each other. So what ends up happening is they continuously kind of move around and they try to find the best sort of situation or orientation where they can maximize the positive attraction, positive negative attraction, and minimize any type of repulsion attractions and minimize anywhere where there's positive near each other and negative sides near each other. So here's an example that let's see here.
Bonds between atoms with different electronegativities have a permanent dipole, that is, a separation of charges, because of the unequal sharing of electrons. Some molecules which contain polar bonds do not have a net dipole. For example, carbon tetrachloride has polar carbon-chloride bonds, but the polarities cancel as a result of its symmetrical structure. It is therefore a nonpolar molecule. Even though the chloroform molecule has a tetrahedral shape, one of the outer atoms is different from the others, so the molecule is not symmetrical. This means the bond dipoles do not cancel, and the molecule has an overall dipole moment. It is polar. Molecules such as sulfur dioxide have asymmetrical structures due to one or more unshared pairs of electrons on the central atom. Sulfur dioxide is an asymmetrical molecule with polar bonds, therefore it is a polar molecule. When polar molecules, such as sulfur dioxide, are close to one another, they tend to align so that the positive end of one molecule points towards the negative end of another molecule. Attractions among polar molecules are called dipole-dipole forces.
So as you see there, and also in this picture, as they kind of move close to another with that attraction between the positive side of one molecule and the negative side of another, they do try to maximize sort of the attraction side of those interactions and minimize repulsion size. But as you can see, obviously, no matter what you do, there's always going to be some, like, positive sides near positive sides, negatives near negatives. But they will sort of continue to kind of move around until energy is really favored for the attraction forces over the repulsion forces. Now, hydrogen bonding is a special type of dipole-dipole. So again, this is still an intermolecular force. And it is a type of dipole-dipole interaction. And it is a bond between hydrogen and some electronegative atom like nitrogen, oxygen, and fluorine. And if you look on the periodic table, or NOF, that is the upper right of the periodic table. And as we talked about with bonding, that is where we find our most electronegative atoms that are held. And that will create a really polar bond. So when hydrogen hooks up with a nitrogen, oxygen, or fluorine, it creates a really polar bond between them. So when hydrogen hooks up with one of those guys, it does create this really polar bond where we get that nice separation of charge where one side's more positive, the other side's more negative, and that helps it tremendously to be able to do this sort of positive negative attraction. So these are called hydrogen bonding, and that is what we see in water. And again, the hydrogen being more positive, the oxygen being more negative. These hydrogens here, really any of these hydrogens, any of these hydrogens can participate in hydrogen bonding because they are directly attached to an oxygen. And that's the important part there. They're directly attached to an oxygen to allow them to hydrogen bond. It's one of those guys there. That's also why, for example, if we took something like ammonia, which is NH3, it also can hydrogen bond, and it has the ability to hydrogen bond because, again, when we look at the hydrogens here, they are directly attached to a nitrogen, right? So these guys could definitely hydrogen bond. Something like HF as well can hydrogen bond because obviously, as you can see here, our hydrogen is directly attached to obviously a fluorine in this case. So all these guys are examples that can hydrogen bond. By the way, they could hydrogen bond with themselves. They could also hydrogen bond with different molecules as well that have the ability to do so. So if you took water and you mixed it with some methanol, which is this guy here, this has our negative positive. This also has our positive negative. So once again, these two guys can hydrogen bond between them, and they're different molecules, but they both have the ability to hydrogen bond, so they're able to interact with each other. That is why something like methanol is actually pretty soluble in water, because they're both using the same type of intermolecular force, so they interact well with each other and can mix really, really well. Now, just because you have a hydrogen doesn't mean that you have the ability to hydrogen bond. So for example, if you took something like methane, which obviously is loaded with hydrogens, has a bunch of hydrogens, this cannot hydrogen bond. And for a couple of reasons, the carbon hydrogen bond there is nonpolar, and these hydrogens here are not attached to a nitrogen, oxygen, or fluorine. So sometimes people think all you need is a hydrogen to be present in order for it to be able to hydrogen bond. But it does need to be a hydrogen that is, again, directly connected to either a nitrogen, oxygen, or fluorine to have the ability to hydrogen bond. That is also why we were talking about dipole-dipole interaction, that those are polar molecules that cannot hydrogen bond, typically will do dipole-dipole. This is the main force for polar molecules that have the ability to hydrogen bond. They're going to hydrogen bond is pretty much the force that they're going to use. So this is the main force for polar molecule and a polar molecule that obviously can hydrogen bond. So they have the ability to hydrogen bond. They're going to do that. Again, if you have a polar molecule that does not have the ability to hydrogen bond, but it's still polar, they will do dipole-dipole interaction. And so that is the slight difference between them, even though technically they're both dipole-dipole. But that is the major difference between them. Any questions on that there? So here's a little bit about hydrogen bonding.
Some polar molecules have unusually strong intermolecular attractions called hydrogen bonding. These attractions occur in molecules where hydrogen is bonded to fluorine, oxygen, or nitrogen. The interaction occurs between the hydrogen of one molecule and an unshared electron pair on the more electronegative element in another molecule. The orientation of hydrogen fluoride and water molecules in the liquid states of these substances is determined by hydrogen bonding. The hydrogen atom in hydrogen fluoride is attracted to the fluorine atom on another hydrogen fluoride molecule. Water with two hydrogen atoms and two unshared pairs of electrons can form 4 hydrogen bonds per molecule. In ice, hydrogen bonding leads to a tetrahedral arrangement of water molecules around one another, forming 6-membered rings that leave open channels through the ice structure. In liquid water, the tetrahedral arrangement is not fixed because the molecules are able to move around, and on average, a water molecule is surrounded by 3.4 other water molecules. Hydrogen bonding forces are unusually strong attractions that occur among molecules in which hydrogen is bonded to a highly electronegative atom.
And that's why we see here again some hydrogen bonding happening between different water molecules. And as you can see, it does create a lot of open space, like we talked about with ice, and that's sort of exaggerated when ice comes together. Again, those kind of open spaces between the water molecules. Now, another, this way actually, another type of interaction that sort of falls into this that we kind of have seen is what's sometimes referred to as ion dipole interactions. An ion dipole interactions is between an ion and a polar molecule. And this type of interaction is actually what occurs when we make a solution or we take something like an ionic compound and we dissolve it in water. So, for example, if you took sodium chloride and you dissolved it in water, this is basically what is happening that allows it to dissolve. And we know that the sodium ion will break apart and the chloride ion will break apart. So what ends up happening is the water molecule with its negative side will go around and basically surround the positive ion through the negative side of water. And the different water molecules will actually surround the negative ion around its positive side, which is the hydrogen side of water. And what this does is kind of twofold. This is really the interaction of an ion and a polar molecule. It's still a positive negative attraction that's occurring. And this is how something like sodium chloride dissolves, is this interaction here. You help this along by mixing it. So you add some energy, you throw a bunch of water molecules around the solid, and that helps kind of pluck off all the ions. Remember that this is a physical change, and we know that because if we heat this up, all the water molecules will go away and the two ions will come back together, and you will see your solid come back. And the reason it looks like maybe it all disappears is there's just so many water molecules surrounding the ions that it is no longer visible to your eye, your naked eye, to be able to see the solid still in that kind of solution because all the ions are basically surrounded and hydrated with a lot of water molecules. So this type of interaction is the interaction that we typically see when we dissolve like a solid in water or something like that to make a solution is like an ion dipole interaction. Any questions on that there? Now, the next type of interaction is what is known as dispersion forces. And dispersion forces are pretty much very weak type of forces. They are the ones that nonpolar molecules basically interact with other nonpolar molecules or themselves as well. So this is the main type of force for when two nonpolar molecules together. Again, they don't have to be different nonpolar molecules. It could be the same nonpolar molecules or different nonpolar molecules. And dispersion forces are really weak type of forces because frankly, if you think about a nonpolar molecule, this is it. They have no charge because electrons are shared equally. And that makes it really hard for nonpolar molecules and nonpolar molecules to do the positive negative thing because they don't have a positive side or a negative side. So there's actually two ways that this can sort of occur. One way that this could occur is what is known as an instantaneous dipole. And what that means is in an instantaneous dipole, you have a nonpolar molecule, maybe next to another nonpolar molecule. And because each of these molecules have electrons that are flying around, all the electrons can end up maybe on one side of the molecule versus the other. That is what is known as polarizability. And that is the ability of electrons to kind of go to one side of the molecule over the other and cause a temporary charge in that nonpolar molecule. So if all the electrons decided to vacation to the left-hand side of the molecule, that left-hand side of the molecule will now be more negative. The other side will become more positive where it normally doesn't have that. And if that molecule happens to be still sitting next to a nonpolar molecule, the electrons in this guy is going to decide, oh, there's like a positive charge. Let's head that way. And now this second nonpolar molecule that normally doesn't have a charge will now technically and temporarily gain a charge. And now you have two nonpolar molecules that normally don't have charges now have temporarily gained those charges because the electrons kind of moved around. And now they have definitely a place where they can interact with each other. Now, these are really weak interactions because just like any vacation you take, right? Eventually you got to go home, right? And eventually these electrons are going to kind of go back away from that situation and they're going to kind of break apart and form new interactions and break apart and form new interactions. So these are very weak interactions. Because of that, they have to rely upon something happening. Another way that you can do that is what is known as an induced dipole interaction. And that's basically, you could kind of make the same sort of thing happen if you roll upon a polar molecule next to a nonpolar molecule. So if you do this situation, the electrons in this guy is going to temporarily go that way. And now you have a way in this polar molecule to interact with this nonpolar molecule. And once again, this is a temporarily type of situation as those electrons can kind of bounce back and the polar molecule can kind of float away a little bit and allow it to sort of go back. This is why, for example, when you try to mix water with oil, which is nonpolar and polar, they do not mix because something that's nonpolar is going to try to use dispersion forces. Something like water is going to use hydrogen bonding. Those are very, very different types of interactions. They cannot maintain that over a long period of time. That's like when you take your oil and vinegar salad dressing, you mix it up, right? It stays mixed for a bit. But if you leave it sit there, eventually everybody separates out from each other. They have no way to maintain that interaction. So this is a very weak sort of intermolecular force.
Solid carbon dioxide, dry ice. Nonpolar molecules are arranged close to one another in a regular array where they move slightly around an average position. The distribution of electrons in a molecule can occasionally become asymmetrical, leading to the formation of a temporary separation of charges, a dipole. Partial changes on the molecule that form a temporary dipole then influence the electron clouds of nearby molecules. Although the dipoles are temporary, there is a significant attractive force between adjacent molecules as a result of the deformation of their electron clouds. These attractive forces are called London dispersion forces. London dispersion forces are the only type of intermolecular force found in nonpolar molecules.
So this is sort of what we were talking about there, that sort of instantaneous dipole that occurs given it that temporary attraction. Now, when we think about our intermolecular forces, just to summarize here and finish up, we basically have hydrogen bonding, we got dipole-dipole interaction, and we got dispersion forces. And when we talk about hydrogen bonding, that is for polar molecules and polar molecules that can hydrogen bond, like our water. And that is the strongest interaction you could kind of have in terms of intermolecular forces. Dipole-dipole is for polar molecules plus polar molecules that cannot hydrogen bond. So an example, CH3, say Cl, so something that looks like this. That's going to be a polar molecule, and that's still relatively strong as well. And dispersion forces are for their nonpolar plus nonpolar molecules. And these are going to be something like, for example, CH4, and this is going to be the weakest. Why is dispersion forces the weakest? It's because it involves nonpolar molecules. They have to have something happen for them to be able to do that interaction. When you have a polar molecule, it is good to go because it always has a positive side, negative side. It doesn't need anything to happen to it because it always has those two sides, and that makes it relatively strong. Now, in terms of dispersion forces, because it is the weakest type of intermolecular force, the strength of dispersion forces actually increases with molar mass. So the more molar mass something has, if it's using dispersion forces, we'll have higher boiling points and melting points because more molar mass means more electrons, greater opportunity for that interaction to occur. And so it does increase with it. So again, these things are responsible for how molecules interact with each other. Uh, Even polar molecules can do dispersion forces, but it is not their main type of interaction. So you really shouldn't put dispersion forces for something that's polar. It's not really its main type of interaction. It will either be dipole-dipole or hydrogen bonding. Any questions on that?